Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of boundary layer theory. Actually, the concept of boundary layer theory is very important in our day-to-day life in many applications. Along with the fluid mechanics, many applications are there like heat transfer or automobile, aeroplane. So many applications are there of this boundary layer theory. So here I'll write some applications of this boundary layer theory in the heat transfer. In the heat transfer application, suppose we have some cold fluid and a hot fluid is there. So the application in the cold fluid and the hot fluid, where we'll get the application? Suppose some kind of boundary formation will be there near to the hot and cold fluid. Okay, so this is one application. Hot and cold fluid, a thin layer formation will be there, a thin layer of air, thin layer of air. Okay, so near to this one. And similarly, I'll give another one example of this, like the drag force and the drag and lift force of an object, force of an objects, okay, which is moving through fluids, or simply you can say the drag and lift of an object when it is moving through the fluids. Similarly, applications of this also there in the area of automobile. In the area of automobile, when the car is moving or when the car is running over a road, so you can see how the air is passing through over the car. So that is one. And similarly, same case also in the case of aeroplane also. So there are many applications are there in this boundary layer theory. So first let's try to understand what is this concept of boundary layer theory. Actually, this concept was initially developed by a scientist called Ludwig Prandtl. A scientist which name is Ludwig Prandtl. He developed this concept of boundary layer theory in the year of 1904. Okay, now what these concepts talks about the fluid. Now this concept actually describes the thin layer of fluid, which is formed near to the surface, and the viscosity or the viscous effect need to are significant, then only this layer formation will be there. So how we can develop this thin layer of this? So let me tell you, we need to consider a real fluid. So when a real fluid flows over a solid object, over a solid body or solid wall, or I can say a solid wall. So the fluid particles will be adhered to the boundary. Okay, the fluid particles, you can say the fluid particles adhere to the boundary, or you can say it is in contact with the boundary of the surface. So that the no slip condition occurs here. So that we can say no slip condition. So that no slip condition occurs here. So what is the meaning of this no slip condition? So no slip condition means nothing but the velocity of the fluid near to the boundary will be 0. So this is no slip condition. So I'll tell you in details about this no slip condition. Let's come to this picture first. Let's try to understand this diagram. Suppose the diagram is actually situated it is situated inside a water flow. Okay, so water is flowing continuously, and this we have taken a solid object. Okay, and this is the solid object which is present here. And when the water is like a fluid is flowing over this surface, like you can see, if you zoom the object, like the fluid flow, you can get a layer formation which is present at this. Okay, in both sides you can see the layer formation can be visible in the both side. Okay, because here also liquid is there, that will be also continuously flows. Now if you see this layer, actually as per the definition, no slip condition. So the no slip condition means what? Now the fluid also, like see, this is the layer formation what we'll get. But above to this layer, we have free stream velocity, because this fluid is flowing with a velocity of u, and that is capital U. Let me write u, or sometimes it is called u infinite. So this is actually free stream velocity. This is called free stream velocity. Okay, and the velocity which is present between the surface and this layer, that is called actually small u, or we can say this is local velocity. This is called local velocity. Now, as I told you, as per the definition, what I told you, near to this boundary layer, near to the surface of this boundary, the velocity is considered as 0. Okay, or we can say this is no slip conditions considered. Why the velocity near to the boundary is 0? That is also one reason is there. What is the reason for that? If you see the boundary, the solid object what we have taken, that is a solid object, correct? And the fluid which is flowing, that is a liquid. So the fluid, let me write here. It is u equal to 0 near to the boundary. This is happening due to the intermolecular forces. This is happening due to the intermolecular bonding, we can say, or intermolecular forces, okay, which is present between the liquid and solid body. So what is the force actually? The force is nothing but it's called as, that is adhesive force. So that is called adhesive force, because this is the liquid which is flowing here over the surface. So when the liquid is flowing, due to this, the molecule which is present in the liquid and the molecules which is present in the solid, okay, there is a adhesive force will be created between this. So if you consider only liquid up to the contact, the liquid is having what? Cohesive force. The liquid is having cohesive force. That means the intermolecular bonding between the molecules in the liquid. So when it is coming in contact with the solid body, so the adhesive forces will be created. And here the adhesive forces is more than the cohesive force. So that's why it will oppose the fluid, and that's why here we won't get any kind of velocity of fluid flow. So that the velocity near to the boundary will be 0. That is u equal to 0, and that is called local velocity. Now similarly, see, it will take a process, it will take some time. So how this boundary layer formed? Now near to the boundary, if I draw here, actually this boundary is there. This is the boundary of solid body. Okay, when the liquid is flowing here, and it will come here like this. Okay, so at this point we will get 0. Now if you come to the next layer, so slowly the impact of, or the effect of boundary will be reduced, so that will get some increment in the velocity. That means here if you get u equal to 0, then the next layer will get the velocity of 1 meter per second maybe, or maybe you will get next to that 1.5 meter per second or 2 meter per second. So slowly we can see the velocity of the fluid increases. Okay, similarly if you come to the next one, here also again similarly we can get something like this. So here let me draw a point here. I'll tell you what is the point. Here I'll get a point, here I'll get a point. So that means as you move along the directions, we'll get a point where the local velocity will be equal to u infinite, or u. The local velocity will be equal to the free stream velocity. So that equalize of this local velocity to the free stream velocity. So along with the path, it will be started increasing, like So now let me show you here. If I can get a point, suppose at this point, then I can get a point here. So if you draw all this point, if you join all this point, in top and bottom side, then we can get a layer like this. We can get a layer. So how this point we got, I told you here. Okay, so this is called actually boundary layer. This is called boundary layer. So at this layer we have the value of u small u equal to capital U or U infinite. That means at this layer, the local velocity which is present inside the boundary layer, that is equal to the free stream velocity. So above to this, all these fluids are U, and inside this, the fluid velocity is small u, and near to the boundary, the velocity of this local velocity is 0. Okay, why it is 0? Because due to this reason. Okay, now the next point is, so you can see there is a change in velocity in the vertical direction along the y direction. You can say the change in velocity from the surface level to this boundary layer. So here, as I told you, that the velocity is increasing slowly like this. So it will give a parabolic formations of this. That means this is the velocity profile. So if you draw, you'll get a velocity profile like this. So at this point, as I told you, u equal to u infinite. But up to this, we can see there is a change in velocity. There is a change in velocity. So that is called actually velocity gradient. That is called velocity gradient. So du by dy. du equal to what? What is the value of u2 minus u1 or u3 minus u2? Because number of velocities are present in this layer. Here is suppose u0, u1, u2, u3, u4, like that number of velocities are there. So layer to layer, the velocity values are changed with respect to the distance. That means the distance between these two layers. So this also we can write y2 minus y1. So this concept already you have discussed previous lecture, like Newton's law of viscosity. If you have seen, there we already discussed. So this is the velocity gradient. So due to this velocity gradient actually, okay, we can see there is a change in velocity. Okay, so the fluid exerts a shear stress. The fluid will exert a shear stress on the wall. So shear stress is equal to what? Tau. So to find out this shear stress, we know one formula, tau equal to mu into du by dy. This is as per the Newton's law of viscosity. We can write this. So tau is the shear stress, mu is the viscosity, and du by dy is the velocity gradient. So this shear stress will be occur inside this boundary layer. Inside this boundary layer, we can find this. Okay, above to this boundary layer, we won't get anything. So above to this boundary layer, what will be there? So here we'll get some value so that we can find out some shear stress. That means shear stress exists in between this boundary layer. Above to this boundary layer, what? Above to this boundary layer, your u small u equal to capital U. So at this layer actually, at this layer, above to this layer, there is no value, there is no existing of this u small u local velocity. After that, you will get only the free stream velocity small capital U. That means there is no change in velocity gradient. There is no change in velocity layer. So that means the velocity gradient du by dy equal to 0 above to this boundary layer. So if this is 0, then we won't get any kind of shear stress effect there above to this boundary layer. So that means tau equal to 0. This is the main concept of this. So I hope you understand this concept of boundary layer theory. Yeah, anything I have not missed, I think. Because see here, if you see at this boundary layer, one more point also there. At this surface of the solid body, the kinetic energy is totally diminishes or it is negligible. So the kinetic energy what is present at this body, so that is going to be convert the kinetic energy. So what is present in this, that is going to be converted to what? This is pressure energy. Okay, so all the kinetic energy which is present near to the boundary, that is converted into the pressure energy. Because we know that there is no loss of energy, that only energy will be converted from one to another one. That is one point. So this is about, like, you know, the flow over a solid body. Again, open one we have considered. So this kind of boundary layer can be formed any one, like, you know, external and internal. This is I have shown you like in suppose external condition I have shown. Okay, if I consider a automobile, suppose a car is moving. Let's consider a car is suppose moving here. Okay, and the effect of air, suppose this is some kind of slope is there here, and how the air movement is there of this surface. So there we can find out the effect of velocity of air on the surface here. So here also boundary layer will be formed. Okay, so this is, what is this? Now this is about the external effect of the velocity or boundary layer. Now similarly, if you consider the internal one, internal boundary layer also, you can find inside a pipe. If you consider a pipe flow, there internal effect will be there. this is the pipe flow will be there. So you can see the velocity profile of this we can find out like this, because we know that because this is the surface, so here also velocity will be 0, at this surface also velocity will be 0. So at the middle of this pipe we can get the maximum velocity. That's why the velocity profile will be for a closed pipe will be like this. You can draw like this. So this is the basic concept of boundary layer theory. In the next lecture we'll discuss what are the different types of boundary layer formations or separation of boundary layer. We'll discuss in our next lecture. I hope you understand this lecture. If you are having some doubt regarding this, you can give a comment in the comment box. Thank you.